What if I told you that at this very moment, something is passing through our solar system that has scientists questioning decades of established theory? Something moving so fast, behaving so strangely, that the data streaming back from our spacecraft doesn't fit any model we've built to explain how celestial objects should act. Right now, approximately 30 million kilometers from where you're sitting, an object from beyond our sun's influence is making its closest approach to Mars. It's traveling at speeds that would carry it from New York to Tokyo in less than 3 minutes, and every telescope, every orbital sensor, every deep space monitoring station we possess is watching it with an intensity that borders on obsession. This is 3I Atlas, the third confirmed visitor from interstellar space to pass through our cosmic neighborhood, and the more data we gather, the less sense it makes. Here's what should concern you. This object is releasing gases in ratios that violate everything we understand about cometary formation. It's changing brightness in patterns that seem almost rhythmic. Its size fluctuates in our measurements so wildly that estimates range across an order of magnitude. And perhaps most troubling of all, the statistical probability of detecting something this massive as only our third interstellar visitor suggests we've either been incredibly lucky or profoundly mistaken about how common these objects actually are. Among the researchers brave enough to commit to a position, there's a deep division. The majority, perhaps 60%, insist this must be a natural object, however unusual its properties might appear. They argue that our sample size of interstellar objects is so small that we simply don't yet understand the full range of what's possible. But a significant minority, around 40%, refuse to completely rule out the possibility that what we're observing might not be entirely natural. They don't say it loudly, they don't put it in official papers, but in private conversations, in encrypted messages between colleagues, that possibility lingers like smoke that won't dissipate. The chemistry alone should make us pause. 3I Atlas is expelling carbon dioxide at a rate 8 times higher than its water emission, a ratio so statistically abnormal that it falls 6 standard deviations outside the normal range. In scientific terms, that's the equivalent of flipping a coin and having it land on its edge. Possible, yes, but so improbable that it demands explanation. Then there's the matter of its size, which remains maddeningly uncertain despite weeks of observation. Depending on which measurements you trust and what assumptions you make about its reflectivity, 3I Atlas could be anywhere from 300 meters to 5 kilometers across. That's not a minor discrepancy. That's the difference between a large building and a small mountain. How can we be so uncertain about something we're watching this closely? And we haven't even addressed the most uncomfortable question yet. The statistical anomaly of finding an object this substantial as only our third confirmed interstellar detection. Either these visitors are far more common than we realized, and we've been missing them, or we've stumbled upon something genuinely rare, something that perhaps intended to be noticed. 3 competing hypotheses are circulating through the research community tonight. 3 different explanations for what 3I Atlas might be, each with implications that range from fascinating to fundamentally disturbing. The data being collected right now as Mars orbiters track this object during its closest approach could settle the debate decisively. Or it could deepen the mystery in ways that force us to reconsider assumptions we've held for generations. What are those spacecraft seeing as 3I Atlas blazes past the red planet? What details will emerge when Hubble captures it at perihelion, its closest approach to the Sun, in just 3 weeks? And if the measurements still refuse to make sense after all this observation, after all this analysis, what does that tell us about the nature of reality in the space between stars? Before we journey deeper into this mystery, before I show you the data that's keeping astronomers awake at night, I want to hear from you. Drop a comment right now telling me where in the world you're watching from. What time is it there? Are you settling into bed, letting this story carry you towards sleep? Or are you listening during a quiet moment, headphones in, the familiar world around you, suddenly feeling a little less certain? And here's the real question I'm curious about. Do you think we're alone in watching this cosmic visitor? Or is there a possibility, however remote, that somewhere out there, another civilization is observing the same object we are, drawing their own conclusions about what it means? If you find yourself drawn to mysteries that exist at the edge of human knowledge, hit that subscribe button now. Because what unfolds over the next hours of this documentary will challenge your assumptions about what's possible in our universe and what might be moving through the darkness between stars. Now, let's talk about what's actually happening up there tonight. The date is October 3rd, 2025. By the time you hear these words, 3I Atlas will have already made its closest approach to Mars, passing the red planet at a distance that, while safe, is close enough for our orbital instruments to capture unprecedented detail. The spacecraft we've positioned around Mars, orbiters designed to study the planet itself, have all temporarily redirected their attention to this interstellar visitor, because opportunities like this don't come around often. In fact, they've never come around quite like this before. To understand why this flyby matters so much, we need to step back and appreciate just how rare confirmed interstellar objects are. For all of human history, up until very recently, we assumed that everything in our solar system originated here. Every asteroid, every comet, every chunk of rock and ice was born from the same primordial cloud that gave rise to our Sun and planets 4.6 billion years ago. We were a closed system, a cosmic family, with no visitors from outside. Then, in 2017, everything changed. An object designated 1I Oumuamua, the One Eye, indicating it was the first confirmed interstellar visitor, was detected passing through our solar system at a velocity that proved it couldn't be gravitationally bound to our Sun. It was just passing through, a cosmic traveler on a journey that had begun in another star system entirely. The discovery was revolutionary, forcing us to confront the reality that objects from other stellar neighborhoods do occasionally wander into ours. Oumuamua was strange in its own right. Its shape appeared elongated, tumbling through space in ways that suggested either a cigar-like form or perhaps a flat, pancake structure. It accelerated slightly as it traveled away from the Sun, a behavior that could be explained by outgassing, but which some researchers found puzzling given the lack of visible cometary activity. The debate about what Oumuamua actually was continues to this day, though most scientists have settled on natural explanations involving cometary composition and unusual structural properties. 2 years later, in 2019, we detected our second confirmed interstellar visitor, 2I Borisov. This one was much more conventional in its behavior, clearly a comet, outgassing vigorously as it approached the Sun exhibiting all the characteristics we'd expect from such an object. Borisov was reassuring in a sense. It demonstrated that interstellar visitors could be normal, familiar, comprehensible. Not everything from beyond had to be as enigmatic as Oumuamua, which brings us to 3I Atlas, discovered in early 2024 and now passing Mars as we speak. From the moment of its detection, Atlas has occupied a troubling middle ground between Oumuamua's strangeness and Borisov's normality. It exhibits cometary activity. It's definitely outgassing, definitely producing jets of material as volatile compounds on its surface sublimate in the sun's heat. But the chemistry of that outgassing is wrong. The ratios don't match what we see in any solar system comet. And its behavior, while not as bizarre as Oumuamua's, includes peculiarities that resist easy explanation. The object was initially detected by the Asteroid Terrestrial Impact Last Alert System, ATLAS, which gives it the second part of its designation. The 3I prefix marks it as our third confirmed interstellar object. When astronomers first calculated its trajectory, they immediately recognized that its orbit was hyperbolic rather than elliptical, meaning it was moving too fast to be captured by the sun's gravity. Like its predecessors, Atlas was just passing through, on a journey that would carry it back into interstellar space after its brief visit to our solar system. But as observations accumulated over the following months, patterns emerged that didn't fit comfortably into our understanding of what interstellar comets should be like. The outgassing was erratic, showing bursts of activity that didn't correlate well with solar heating. The brightness variations suggested either an irregular shape tumbling through space or changes in activity level that followed no obvious pattern. And then there was that chemistry, that impossible ratio of carbon dioxide to water that sat so far outside the normal range it demanded explanation. Some researchers proposed that Atlas might have formed in a stellar system with very different chemical composition than our own, perhaps around a star with unusual elemental abundances that led to comets with exotic makeups. Others suggested it could be a fragment of a larger body that had been shattered by collision, exposing interior materials that wouldn't normally be visible on a comet's surface. Still others admitted they simply didn't know what could produce the observed characteristics, but they remained confident that some natural process must be responsible. And then there was the minority who wondered, quietly and carefully, whether we might be looking at something that wasn't entirely natural at all. The hypothesis that 3I Atlas might be artificial, or at least not entirely natural, isn't something most scientists are willing to discuss openly. The stigma attached to such speculation is enormous, the potential for career damage significant. But in private communications, in conversations that happen after conferences, when the official proceedings have ended, some researchers admit that the data presents challenges that natural explanations struggle to address. Dr. Michael Zhang, an astronomer specializing in small body dynamics at a major research university, put it carefully in a recorded interview. What we're seeing with Atlas doesn't fit our models cleanly. That doesn't mean it's artificial. It almost certainly means our models are incomplete. But we have to be honest about what the data shows and what it doesn't show. And right now, there are aspects of Atlas's behavior that resist conventional interpretation. That measured language conceals genuine puzzlement, because when you strip away the careful academic phrasing, What Zhang and others like him are saying is that Atlas is doing things it shouldn't be doing, exhibiting characteristics it shouldn't have, following patterns that don't match any known natural process. That doesn't automatically mean intelligence is involved. Nature is endlessly creative, capable of producing phenomena we haven't yet encountered or understood. But it does mean we're operating in territory where our confidence in explanations has become shakier than we'd like to admit. The Mars flyby happening tonight represents a crucial opportunity to gather data that might resolve some of these uncertainties. Mars has become, somewhat inadvertently, an excellent platform for observing interstellar objects. We have multiple spacecraft orbiting the planet, equipped with instruments designed to study Martian atmospheric composition, surface features, and geological processes. But those same instruments can be repurposed to examine passing objects when opportunities arise. The European Space Agency's Mars Express orbiter has devoted observation time to tracking Atlas. NASA's MAVEN spacecraft, designed to study Mars's upper atmosphere, has been capturing spectrographic data on the visitor's composition. Even the Mars Reconnaissance Orbiter, typically focused on high-resolution imaging of the Martian surface, has turned its attention skyward to contribute observations. This coordinated campaign represents an unprecedented level of interplanetary cooperation focused on a single transient target. What are they looking for? Several key questions drive the observation program. First, detailed spectrographic analysis might resolve the mystery of Atlas's unusual chemistry. By examining the exact wavelengths of light absorbed and emitted by the outgassing material, researchers can determine not just what elements are present, but also their molecular forms and physical conditions. This could reveal whether the strange carbon dioxide to water ratio is real or an artifact of earlier, less precise measurements. Second, close observation during the Mars flyby provides a chance to better constrain Atlas's size and shape. By watching how it reflects sunlight from multiple angles as it moves past Mars, astronomers can build a more accurate three-dimensional model of the object. This would finally resolve the uncertainty about whether we're dealing with something building-sized or mountain-sized, a rather important distinction. Third, and perhaps most intriguingly, the orbiters are watching for any changes in Atlas's behavior as it passes through Mars's magnetosphere. The red planet has a weak, patchy magnetic field generated by localized crustal magnetization rather than a global dynamo like Earth's. But even this modest magnetic environment might interact with Atlas in ways that could reveal something about its composition or internal structure. If it's generating its own magnetic field, if it's electrically charged, if there are any electromagnetic anomalies associated with it, the Mars flyby is our best chance to detect them. The data being collected tonight won't be immediately available to the public or even to most researchers. Raw observations need to be processed, calibrated, and verified before they can be meaningfully analyzed. That process typically takes weeks or months, depending on the complexity of the measurements and the care required to ensure accuracy. But preliminary results should begin emerging within days, and those initial findings will shape how the scientific community approaches the even more crucial observation period, coming in 3 weeks. That's when Atlas reaches perihelion, its closest approach to the Sun. At perihelion, solar heating will be at its maximum intensity, driving the most vigorous outgassing and potentially revealing characteristics that aren't visible at greater distances. The Hubble Space Telescope has been allocated observation time during this critical period, bringing to bear one of humanity's most capable instruments for studying distant objects. What Hubble sees could definitively answer lingering questions about Atlas's nature, or it could deepen the mystery in ways we haven't yet imagined. While we wait for data from the Mars flyby to be processed and released, it's worth examining what we already know about Atlas and why it's generated such intense interest among researchers. Let's start with that troubling chemistry, because it really is the heart of what makes this object so puzzling. Comets, as we understand them, are essentially dirty snowballs, mixtures of water ice, frozen gases, and rocky material left over from the formation of a planetary system. When a comet approaches the Sun, solar heat causes these frozen materials to sublimate, transitioning directly from solid to gas without passing through a liquid phase. This creates the characteristic tail of material streaming away from the comet, always pointing away from the Sun due to solar wind and radiation pressure. The composition of cometary outgassing tells us about the conditions under which the comet formed. Different gases freeze at different temperatures, so what's present in a comet reflects the temperature and chemistry of the region where it coalesced billions of years ago. In our solar system, comets formed in the cold outer reaches typically show high water content mixed with carbon monoxide, carbon dioxide, methane, and various other volatile compounds in ratios that reflect the composition of the primordial solar nebula. When we observe solar system comets, objects born in our own stellar neighborhood, we see a fairly consistent pattern. Water is usually the dominant outgassing component, often accompanied by significant amounts of carbon monoxide. Carbon dioxide is present, but typically at lower levels than water. There's some variation, of course, because individual comets formed in slightly different locations and conditions. But the overall ratios fall within a range we've come to consider normal based on decades of observation. 3I Atlas doesn't follow this pattern, not even close. Early spectroscopic observations showed carbon dioxide emission lines that were surprisingly strong relative to water. As more data accumulated, researchers calculated that Atlas was releasing CO2 at roughly 8 times the rate of H2O, a ratio that's essentially unprecedented in cometary science. No solar system comet shows anything like this chemistry. It's so far outside the normal range that statistical analysis puts it 6 standard deviations from typical values. To put that in perspective, if cometary chemistry were normally distributed like height in human populations, finding an object 6 standard deviations from the mean would be like encountering a person who was either 3 feet tall or 12 feet tall. Possible theoretically, but so improbable that if you actually met such a person, you'd reasonably wonder whether you were really looking at a normal human or something else entirely. Several hypotheses have been proposed to explain Atlas's bizarre chemistry, none of them entirely satisfying. The first suggestion was that it might have formed in a region of its parent star system that was unusually rich in carbon dioxide relative to water. Different zones in a protoplanetary disk can have different chemical compositions depending on temperature, pressure, and the specific history of that system. Perhaps Atlas originated from a place where conditions favored CO2 retention, while water was depleted. The problem with this explanation is that it requires rather extreme conditions that don't match well with our understanding of how planetary systems form. Water is one of the most abundant molecules in the universe, composed of hydrogen and oxygen, two of the most common elements. For water to be suppressed relative to carbon dioxide in a comet-forming region requires specific circumstances that seem contrived when you try to model them in detail. A second hypothesis suggests that Atlas might have undergone some kind of processing that altered its surface chemistry. Perhaps it collided with another object, excavating deep interior materials that have different composition than the pristine surface. Or maybe it passed very close to a star at some point in its journey, heating its outer layers and driving off water preferentially, leaving behind a CO2-enriched crust. These scenarios are more plausible, but introduce their own complications. A collision violent enough to significantly alter surface composition should leave other evidence, fragments, debris, irregular shape from the impact. Close stellar passage would require a very specific trajectory and would likely leave thermal signatures we're not seeing. The third explanation, whispered more than stated openly, is that we might not be looking at a natural object at all, or at least not entirely natural. An artificial structure, perhaps a probe or vessel of some kind, might be outgassing deliberately as a propulsion mechanism or cooling system, producing ratios that have nothing to do with primordial chemistry and everything to do with engineering requirements. This would neatly explain why the composition doesn't match natural comets, because it's not a comet, it's something else. Most researchers reject this interpretation, arguing that we shouldn't invoke extraordinary explanations when we simply don't have enough data to properly understand ordinary ones. The universe is vast, they argue, and our sample size of interstellar objects is laughably small, just 3 confirmed visitors. We shouldn't be surprised that the third one shows characteristics we haven't seen before. That's what we should expect when exploring new territory. The strange chemistry of Atlas is a puzzle, certainly, but not evidence of anything more exotic than our incomplete understanding of cometary diversity. And yet, that 6 sigma deviation nags at researchers who spend their careers analyzing data and understanding statistics. 6 standard deviations is really, genuinely, profoundly unusual. It's the kind of result that, in most contexts, would make you question your assumptions or suspect that something non-random is influencing your observations. In particle physics, a 6 sigma result is considered definitive proof of a new phenomenon. In medical research, it would be headline news. In cometary science, it's uncomfortable, difficult to explain, worthy of intense scrutiny. The Mars flyby data will help. By observing Atlas with instruments that can precisely measure the composition and quantity of outgassing material, researchers hope to either confirm the unusual chemistry definitively or discover that earlier measurements were somehow misleading. Maybe there's water present that earlier observations missed, hidden in wavelengths that weren't adequately sampled. Maybe the carbon dioxide emission is more variable than we realized, and we happen to catch Atlas during a period of enhanced CO2 outgassing that doesn't represent its average behavior. These are reasonable possibilities that could resolve the mystery within natural explanations. But if the Mars data confirms what earlier observations suggested, if Atlas really is persistently releasing carbon dioxide at 8 times the rate of water, with no measurement error or observational bias to explain it, then we'll be forced to confront a more fundamental question. What kind of object exhibits chemistry this strange? And what does its presence in our solar system tell us about the nature of the space between stars? Beyond the chemistry puzzle, there's the equally troubling matter of Atlas's physical characteristics, or rather, our inability to pin them down with any confidence. For an object we've been observing for over a year, the uncertainty about its basic properties is embarrassing. Depending on which observations you trust and what assumptions you make, Atlas could be anywhere from 300 meters to 5 kilometers across. That's not a small margin of error. That's fundamental uncertainty about whether we're dealing with something the size of a large building or a small mountain range. How is this possible? How can modern astronomy, with all its sophisticated instruments and computational power, be so uncertain about the size of an object we're actively tracking? The answer lies in the complicated relationship between what we can directly measure and what we can only infer. We can't actually see the physical extent of Atlas directly. It's too far away and too small for even our best telescopes to resolve its actual shape and size. What we can measure is how much light it reflects, its brightness, and from that brightness, we try to work backward to calculate its size. But that calculation depends critically on knowing how reflective the object's surface is, a property called albedo. If Atlas has a bright reflective surface like fresh snow, then a relatively small object could produce the observed brightness. If it has a dark, absorptive surface like charcoal, then it would need to be much larger to reflect the same amount of light. The problem is that we don't know its albedo with any precision. We can make educated guesses based on typical cometary surfaces, but those guesses span a wide range, and Atlas might not be typical. Complicating matters further, Atlas is outgassing, surrounded by a cloud of material called a coma. This coma contributes to the total brightness we observe, making it even harder to determine how much light is being reflected from the solid nucleus versus scattered by gas and dust in the surrounding cloud. Separating these contributions requires careful observation at multiple wavelengths and sophisticated modeling. Different research teams using different techniques have arrived at different estimates, hence the enormous range of possible sizes. Dr. Elizabeth Warren, a planetary scientist who has spent considerable time trying to constrain Atlas's properties, expressed her frustration in a research seminar. We have hundreds of observations from multiple telescopes. We have spectra, photometry, polarimetry, all the data we could reasonably hope for. And yet, we still can't say with confidence whether this object is a few hundred meters or several kilometers across. That tells you something about how unusual Atlas is. Normal objects, even distant ones, don't typically present this level of ambiguity. The Mars flyby offers a chance to narrow this uncertainty significantly. By observing Atlas from Mars' orbit, instruments can measure how its brightness changes as it rotates and as the angle between sun, object, and observer changes. These variations contain information about shape, size, and surface properties. Given multiple observations from different geometries, researchers can build models that much better constrain the physical characteristics. There is also the possibility of radar observation, though this is more challenging. Some spacecraft in Mars' orbit are equipped with radar systems designed to probe beneath the Martian surface. In principle, these radars could be used to actively ping Atlas, bouncing radio waves off its surface and measuring the return signal. Radar provides direct information about size and distance that doesn't depend on albedo assumptions. If such observations were successfully completed during the flyby, they could resolve the size ambiguity definitively. But even assuming the Mars observations successfully pin down Atlas's size, that only solves one piece of the puzzle, because the uncertainty about its physical properties extends beyond mere dimensions. There's also the question of what it's made of, how that material is structured, and whether the object is solid throughout or has internal voids and complexity. The outgassing behavior provides some clues. The fact that Atlas is actively releasing gas means that volatile materials are present either on the surface or in the near subsurface, and that solar heating is able to reach and sublimate these materials. This suggests a relatively porous structure rather than a solid block of rock and ice. Porosity allows heat to penetrate more deeply and provides pathways for gas to escape. But the details of how the outgassing varies over time hint at something more complex than a simple porous snowball. Atlas shows bursts of enhanced activity that don't correlate well with changes in solar heating. Sometimes it brightens significantly over short periods, suggesting increased gas and dust production, then settles back down to lower activity levels. These variations could indicate that we're seeing active vents or jets on specific parts of the surface that become more or less active as the object rotates, exposing different regions to sunlight. Or they could indicate something else entirely. Internal processes unrelated to solar heating, perhaps radioactive decay warming the interior, or chemical reactions between different materials, or even deliberate venting from some kind of controlled system. That last possibility returns us to the uncomfortable question of whether Atlas might be artificial, a question most researchers prefer to avoid, but which refuses to be completely dismissed. What would an artificial interstellar object look like? How would it behave as it passed through a solar system? We have no template for this, no experience to guide our expectations. But we can make some educated guesses based on our own emerging capabilities in space exploration and our understanding of physics. If a civilization wanted to send a probe to another star system, the journey would take an enormous amount of time, even at very high speeds. The nearest star to our Sun is over 4 light-years away. Even traveling at a significant fraction of light speed, something we're nowhere close to achieving, the journey would take years or decades. More realistic velocities would extend the travel time to centuries or millennia. Any probe making such a journey would need to be robust enough to survive that duration, autonomous enough to function without real-time control, and efficient enough with its energy budget to remain operational after such an extended voyage. It would probably need some kind of protective shell or casing to shield sensitive instruments from cosmic radiation and micrometeorite impacts during the long journey. It might use the material of that shell or outer layers as propellant if it needed to make trajectory adjustments. And it would likely need to manage thermal conditions carefully, perhaps venting waste heat or adjusting its orientation to control solar heating. In other words, an artificial interstellar probe might well appear to be a rocky or icy object with unusual outgassing behavior, strange chemistry reflecting its engineered composition rather than natural formation, and size uncertainty due to complex structure that doesn't fit simple models. It might look, in short, rather like Atlas. This doesn't mean Atlas is artificial. It means that if we stumbled across an artificial probe, we might have difficulty distinguishing it from a strange natural object, especially if the probe was designed to be somewhat camouflaged, or if it had simply degraded over its long journey to the point where its artificial origins were no longer obvious. The statistical argument is perhaps the most troubling aspect of the Atlas mystery, and it's one that doesn't get enough attention in public discussions of the object. Put simply, if interstellar visitors are rare, finding one as interesting as Atlas among only our third confirmed detection is suspicious. If they're common, then we've been missing most of them, which raises questions about our observational capabilities and assumptions about what we're looking for. Let's break this down carefully. Prior to 2017, we had never definitively detected an interstellar object passing through our solar system. Then we found Oumuamua, then Borisov, now Atlas. 3 confirmed detections in about 8 years. This might suggest that such objects pass through fairly frequently, perhaps several per year or even more, but that we only notice the ones that happen to pass close enough to Earth at the right time when our telescopes are pointed in the right direction. If that's the case, then the space between stars is much more populated with wandering objects than we previously thought. Every star system must be ejecting countless comets, asteroids, and planetary fragments into interstellar space over its lifetime. These ejected objects would fill the galaxy, creating a background population of interstellar wanderers that occasionally stumble into other star systems by chance. Under this scenario, finding an unusual object like Atlas isn't particularly surprising. If there are many interstellar visitors passing through, then by random chance, some of them will have strange chemistry, odd outgassing patterns, ambiguous sizes, and other peculiar characteristics. The galaxy is vast, stellar systems are diverse, and formation conditions vary enormously. We should expect variety among interstellar objects, including examples that stretch or violate the patterns we've observed in our own solar system. But there's a problem with this reasoning, and it relates to the size uncertainty we discussed earlier. If Atlas is on the larger end of the size estimates, several kilometers across, then it's a really, genuinely massive object. Objects that large are rare even within solar systems. Finding one as an interstellar visitor, particularly as only our third detection, becomes statistically implausible unless interstellar space is absolutely teeming with large wandering objects. Dr. James Patterson, who has modeled the expected population of interstellar objects based on stellar ejection rates and galactic dynamics, put it bluntly in a conference presentation. If Atlas is as large as some estimates suggest, then either we've been extraordinarily lucky to detect it so early in our search for interstellar visitors, or there's a selection effect we don't understand that makes large objects more common in interstellar space than theory predicts, or, and I say this with great hesitation, Atlas isn't a random ejected object, but something that was specifically sent into our solar system. That last possibility is the one that makes most scientists deeply uncomfortable. The idea that Atlas might be a deliberate visitor, a probe, a message, a signal from intelligence beyond Earth, carries implications so enormous that the burden of proof required is correspondingly high. Extraordinary claims require extraordinary evidence, and so far, the evidence remains ambiguous enough that natural explanations, however strained, remain tenable. But the statistical puzzle won't go away. Either interstellar space is much more crowded than we thought, or we've been remarkably fortunate in our detections, or something about Atlas's trajectory brought it into our solar system for reasons that aren't purely random. The Mars flyby data won't resolve this statistical question directly, but it might provide additional clues about Atlas's nature that help us evaluate which scenario is most likely. Consider what happens if the Mars observations reveal that Atlas is indeed on the larger end of size estimates, say several kilometers across. That would make the statistical coincidence of finding it so early even more striking. It would strengthen the argument that there's something non-random about its presence, though what that something might be remains unclear. Perhaps large interstellar objects are more common than theory suggests because ejection mechanisms preferentially expel bigger bodies. Perhaps we're more likely to detect larger objects because they're brighter and easier to spot, creating an observational bias. Or perhaps, and this is the possibility that won't quite disappear, Atlas is large because it needs to be, because it's carrying something or serving some purpose that requires substantial mass. Conversely, if Mars data shows Atlas is smaller in the hundreds of meters range, then the statistics become less troubling. Small objects should be much more numerous than large ones, so finding a small interstellar visitor early in our search is less surprising. The strange chemistry and other anomalies would still require explanation, but the overall picture would fit more comfortably within natural expectations. While we await the processed data from tonight's Mars flyby, it's worth stepping back to consider the broader context of how we search for and identify interstellar objects. Because the detection of Atlas, like its predecessors, wasn't a simple matter of pointing a telescope skyward and spotting something unusual. It required sophisticated automated systems, careful analysis, and a bit of luck. The Asteroid Terrestrial Impact Last Alert System, ATLAS, that gave our visitor its name, consists of multiple telescope installations designed to scan the entire visible sky every night. These aren't the massive research telescopes you might picture when you think of astronomy. They're relatively small instruments, half-meter mirrors, but they're optimized for a specific task, detecting moving objects that might pose a threat to Earth. Every clear night, ATLAS telescopes capture images of the sky in overlapping fields, then compare those images to reference catalogs of known stars and galaxies. Anything that moves between observations, asteroids, comets, satellites, shows up as a streak or appears in different positions in successive images. Software algorithms identify these moving objects automatically, flagging them for further analysis. Most of what ATLAS detects is mundane: known asteroids in their predictable orbits, satellites crossing the field of view, occasionally a previously unknown near-Earth asteroid that requires follow-up to determine if it might pose a collision risk. But very rarely the system catches something that doesn't fit the pattern of objects bound to our solar system, something moving too fast, on a trajectory that can't be explained by solar gravity alone. That's what happened in early 2024 when the object we now call 3I Atlas was first detected. Initial observations showed a faint object moving across the sky at a rate that seemed inconsistent with typical asteroid motion. Follow-up observations by larger telescopes confirmed the unusual trajectory and began the process of determining whether this was truly an interstellar visitor or some kind of solar system object on a highly unusual orbit. The key measurement is orbital energy. Objects bound to the solar system have negative orbital energy. They're trapped in the sun's gravitational well, endlessly circling in elliptical orbits. Objects from interstellar space have positive orbital energy. They're moving so fast that solar gravity can't capture them, can only bend their paths slightly before they exit the system on hyperbolic trajectories. Calculating orbital energy requires precise measurements of an object's position over time. Too few measurements or measurements with too much uncertainty can lead to ambiguous results. In the early days after Atlas's discovery, there was some debate about whether it might be an extremely eccentric solar system comet rather than a true interstellar visitor. But as more observations accumulated from telescopes around the world, the trajectory became clear, hyperbolic, definitely unbound, certainly interstellar. Once that was established, the object became a high priority for observation by major telescopes. Time was allocated on Hubble, on ground-based facilities, on infrared telescopes and radio arrays. Every available instrument that might contribute useful data was brought to bear, because interstellar objects don't linger. They pass through quickly, and once they're gone forever. The window for detailed study is brief. That urgency drives the intensity of observation around events like tonight's Mars flyby and the upcoming perihelion passage. These are opportunities to capture data under conditions that won't be repeated. Mars flyby provides close-range observation from multiple spacecraft with diverse instruments. Perihelion provides maximum solar heating and likely peak outgassing activity. Miss these chances, and we miss our best opportunities to understand what Atlas actually is. The question of what happens after perihelion is also significant, though less discussed. Once Atlas swings around the Sun and begins heading back out of the solar system, will we continue to observe it? Can we track it all the way to the edge of the solar system and beyond? And more intriguingly, will we attempt to send a mission to intercept it? The idea of a dedicated mission to an interstellar object has been discussed in the planetary science community for years, ever since Oumuamua's detection and the realization that such visitors occur more frequently than previously thought. The challenge is timing and delta V, the change in velocity required to match trajectories with a fast-moving interstellar object. Interstellar visitors are, by definition, moving at velocities well above what solar system objects typically exhibit. They're not bound to the Sun, so they're not following the relatively sedate orbital speeds of planets and asteroids. They're screaming through at speeds that reflect their origin from somewhere else, carrying kinetic energy from whatever gravitational assist or ejection event sent them on their interstellar journey. Catching up to such an object requires enormous amounts of fuel or extremely efficient propulsion systems. You have to accelerate your spacecraft to match the visitor's velocity, or at least get close enough that you can make meaningful observations during a brief flyby. With current propulsion technology, This is extraordinarily difficult. By the time we've detected an interstellar object, calculated its trajectory, designed a mission, built and launched a spacecraft, the object is typically already too far away to catch. Oumuamua was gone before we could mount any kind of mission. Borisov was detected with more advance notice, and there were serious proposals for rapid response missions that might have intercepted it. But funding and technical challenges prevented those missions from happening. Now we have Atlas, and once again, the discussion of a mission is circulating through planning committees and funding agencies. The advantage this time is advance notice. Atlas was detected in early 2024, giving more than a year of warning before its perihelion passage. In principle, a rapidly developed mission launched in late 2024 or early 2025 might be able to intercept Atlas as it exits the solar system, though the technical challenges remain formidable. Such a mission would need to be simple. No complex instruments or ambitious science objectives. Just get to the object and capture whatever data basic sensors can provide during a brief encounter. But even a simple flyby mission to an interstellar object would provide data of immense value. Close-range images would resolve the size ambiguity definitively. Spectrometers could analyze the composition of outgassing material with far greater precision than Earth-based or orbital telescopes can achieve. Mass spectrometers might directly sample the gas and dust in Atlas's coma, determining not just what elements are present, but their isotopic ratios, information that would reveal the object's formation environment with much greater certainty. And, perhaps most significantly, close-range observation might settle the question of whether Atlas is entirely natural, or whether it exhibits characteristics suggesting artificial origin. Surface features, structural regularity, evidence of manufacturing or design. These would be much more apparent in high-resolution images taken from nearby than in the fuzzy, ambiguous observations we can make from Earth. As of now, no mission to Atlas has been officially approved or funded, though proposals exist and are being evaluated. The decision will likely depend on what the Mars and perihelion observations reveal. If Atlas continues to appear strange but arguably natural, the case for a dedicated mission becomes harder to make. Why spend hundreds of millions of dollars to visit one peculiar comet when we could use those resources to study multiple objects closer to home? But if the upcoming observations reveal characteristics that can't be easily explained by natural processes, if the chemistry remains inexplicable, if the size and structure suggest complexity beyond what comets should have, if any of the more exotic possibilities start to seem less remote, then the pressure to mount a mission will intensify dramatically. Because if there's even a small chance that Atlas is something other than a natural object, the imperative to study it closely before it leaves our solar system becomes overwhelming. This brings us to a question that underlies all the scientific speculation and analysis. What would it mean if Atlas is artificial? What implications would that have for humanity's understanding of our place in the universe? The detection of extraterrestrial intelligence, or even just extraterrestrial technology, would be the most significant discovery in human history. It would confirm definitively that we're not alone, that intelligence and technological capability have emerged elsewhere in the cosmos. It would immediately raise questions about the prevalence of such intelligence. Is it common with technological civilizations scattered throughout the galaxy? Or is it rare with vast distances separating the few instances where it has arisen. It would also raise questions about intent and communication. If Atlas is a probe, what is it probing? Is it simply gathering data about planetary systems it passes through, an automated scientific mission launched by some long-dead civilization? Is it searching for signs of intelligence? And if so, has it found any evidence of human civilization during its passage through our solar system? Is it capable of reporting back to its creators? Or has it been traveling for so long that the civilization that built it no longer exists? These questions would dominate public discourse and scientific inquiry for generations. Every aspect of Atlas would be studied in exhaustive detail, searching for any clue about its purpose and origin. The discovery would force us to confront our assumptions about intelligence, consciousness, and the likelihood of life elsewhere in the universe. It would inspire some and terrify others, unite humanity in shared wonder, or divide us in disagreement about what the discovery means and how we should respond. But we're getting ahead of ourselves. The much more likely scenario is that Atlas is natural, strange, certainly, unprecedented in some respects, absolutely, but ultimately explicable through physics and chemistry once we have sufficient data and understanding. The universe is vast and old, and it has had ample time to produce objects with characteristics we haven't encountered before. Our experience is limited, our observations incomplete. What seems impossible might simply be improbable. What seems designed might simply be unusual. Still, the questions persist. That 6 sigma chemistry anomaly, the size uncertainty, the statistical unlikelihood of finding such an object so early in our survey of interstellar visitors, the outgassing behavior that doesn't quite fit models, the brightness variations that hint at complexity. Individually, each anomaly might be explainable. Collectively, they create a pattern of strangeness that refuses to resolve into comfortable clarity. And that's where we find ourselves tonight, as Mars orbiters track Atlas during its closest approach to the red planet, as instruments capture data that might finally provide answers, or might only deepen the mystery. We're in a moment of suspension, waiting for information that could shift our understanding significantly in one direction or another, natural or artificial, common or rare, explainable or inexplicable. The data will tell us, or at least it will move us closer to answers. Science rarely provides absolute certainty, but it does provide increasing confidence as evidence accumulates. Each observation constrains the possibilities, eliminates hypotheses that don't fit, strengthens explanations that do. The Mars flyby is one more critical data point in our attempt to understand what Atlas is and what its presence in our solar system means. While the scientific instruments do their work and researchers begin the careful process of analyzing Mars flyby data, it's worth considering how the public has responded to Atlas and what that response reveals about humanity's readiness for potential contact with extraterrestrial intelligence. The reaction has been surprisingly muted compared to what one might expect. When Oumuamua was detected in 2017 and its unusual characteristics became apparent, there was a brief flurry of public interest and speculation. Some astronomers, most notably Dr. Avi Loeb of Harvard, publicly suggested that Oumuamua might be artificial, a possibility that generated headlines and vigorous debate. But after a few weeks, public attention moved on to other concerns, and Oumuamua faded from popular consciousness even as researchers continued to puzzle over its properties. Borisov in 2019 generated even less public excitement, perhaps because it appeared more conventionally cometary and thus less mysterious. The fact that it was an interstellar visitor, a piece of another star system passing through ours, seemed less captivating to the general public than the strange characteristics of Oumuamua had been. Now we have Atlas, arguably stranger than Oumuamua in some respects, certainly more active and observable than either of its predecessors. Yet public awareness remains limited, largely to those who follow astronomy news closely. There haven't been major media campaigns or widespread discussion about what Atlas might be. Most people remain completely unaware that an interstellar visitor is currently passing Mars and approaching the Sun, carrying mysteries that challenge our understanding of what's possible. This muted response is interesting and perhaps somewhat concerning. It suggests that humanity has become somewhat desensitized to cosmic discoveries, that the extraordinary has become ordinary through repetition. We live in an age of remarkable astronomical revelations, exoplanets discovered by the thousands, black hole images captured, gravitational waves detected, and each discovery competes for attention in an information environment saturated with competing stimuli. Or perhaps the muted response reflects something more fundamental, a sense that interstellar visitors, however interesting scientifically, don't directly impact daily human life. They're remote curiosities, objects of academic interest, but not immediate relevance to the concerns that occupy most people's attention. Unless Atlas does something dramatic, changes course obviously, emits a clear signal, approaches Earth dangerously, it remains in the category of interesting space news rather than urgent global concern. But there's a subset of the public that is paying very close attention, and their response reveals both the fascination and the anxiety that encounters with the unknown can generate. Online forums dedicated to space exploration and the search for extraterrestrial intelligence have been actively discussing Atlas since its discovery. Speculation ranges from sober analysis of the scientific data to wild theories about its origin and purpose. Some see Atlas as potential evidence for panspermia, the hypothesis that life or its precursor molecules might spread between star systems on objects like comets and asteroids. If Atlas formed in a system where life emerged, it might carry organic molecules or even dormant microorganisms in its ice. Its passage through our solar system could theoretically deliver such materials to planets or moons, where they might find environments suitable for survival or growth. Others interpret Atlas's unusual characteristics as possible evidence of the zoo hypothesis, the idea that advanced civilizations might be observing us while deliberately avoiding direct contact, perhaps as we might observe animals in a wildlife preserve without interfering. In this view, Atlas could be an observation probe, gathering data about our solar system and its inhabitants while maintaining the appearance of a natural object to avoid causing disruption. Still others take a darker view, seeing Atlas as a potential precursor to something more ominous. In this interpretation, the unusual chemistry and behavior might indicate a probe assessing our solar system for resources, habitability, or strategic value. Its passage could be reconnaissance preceding more direct contact or intervention. This perspective tends to be most common among those who view the cosmos through a lens of competition and conflict, who assume that any sufficiently advanced civilization would be expansionist and potentially threatening. The scientific community generally regards these speculative interpretations with skepticism, and rightly so. The burden of proof for extraordinary claims is high, and Atlas's unusual characteristics, while puzzling, don't constitute proof of anything beyond our incomplete understanding of interstellar object diversity. Natural explanations remain viable, even if they require stretching our models of cometary chemistry and behavior. Yet the fact that these discussions are happening at all, that a significant number of people are seriously considering the possibility that Atlas might be artificial or biologically significant, reveals something important about where we are as a species. We're beginning to internalize the reality that we live in a universe potentially teeming with other forms of intelligence, that contact with extraterrestrial life or technology is a genuine possibility rather than pure science fiction. This shift in perspective has been gradual, building over decades as our understanding of the cosmos has deepened. The discovery of exoplanets, planets orbiting other stars, has been particularly significant. We now know that planetary systems are common, that many stars host worlds where conditions might be suitable for life. This knowledge transforms the question of extraterrestrial intelligence from "could they exist?" to "where are they and how do we find them?" The Drake equation, formulated in 1961 by astronomer Frank Drake, attempts to estimate the number of active, communicative, extraterrestrial civilizations in our galaxy by multiplying together various factors: the rate of star formation, the fraction of stars with planets, the number of planets per system that could support life, and so on. Early estimates using this equation varied wildly depending on the assumptions made about each factor. But as our knowledge has improved, some of those factors have become less uncertain. We now know that most stars have planets. We know that planets in the habitable zone where liquid water could exist are relatively common. We know that the basic chemistry of life, organic molecules, forms readily in space and has been detected in comets, asteroids, and interstellar clouds. These discoveries have generally shifted estimates toward higher numbers of potential sites where life might arise. Yet we still haven't detected any clear evidence of extraterrestrial intelligence. No radio signals that are unambiguously artificial. No obvious megastructures or signs of large-scale engineering. No visitors that are definitively technological rather than natural. This apparent contradiction, the universe seems suitable for life, yet we see no evidence of it, is known as the Fermi paradox, after physicist Enrico Fermi, who famously asked, "Where is everybody?" Many solutions to the Fermi paradox have been proposed. Perhaps intelligence is much rarer than we think, requiring such specific conditions that Earth might be unusual or even unique in our galaxy. Perhaps technological civilizations tend to destroy themselves before achieving interstellar capability. Perhaps the distances between stars are simply too vast for practical travel or communication, leaving civilizations isolated despite their abundance. Perhaps advanced civilizations deliberately hide their presence, or exist in forms we don't recognize and aren't equipped to detect. Or perhaps we simply haven't been looking long enough or carefully enough. Our radio searches for extraterrestrial intelligence have been ongoing for only about 60 years, a tiny fraction of cosmic time. Our ability to detect exoplanets and analyze their atmospheres for biosignatures is only a few decades old. We've only confirmed 3 interstellar objects passing through our solar system. Our sample size is small, our methods are still developing, and our patience may not have been adequately tested. Atlas enters this context as another data point in our ongoing attempt to understand our cosmic neighborhood and our place within it. Whether it's natural or artificial, its presence reminds us that the space between stars isn't empty, that our solar system isn't isolated, that we're part of a dynamic galactic environment where materials and possibly even information flow between stellar systems over vast timescales. If Atlas is natural, the most likely scenario, it still provides valuable scientific information. It tells us about the chemistry and physics of another planetary system, about the materials available, and the conditions present during its formation. By studying interstellar visitors, we're essentially conducting remote geology and chemistry on systems we could never hope to visit directly. Each object is a sample returned from the cosmos, carrying information encoded in its composition and structure. If Atlas is artificial, the remote but non-zero possibility, then it represents something far more profound, contact with intelligence beyond Earth. Not necessarily direct communication or interaction, but at minimum confirmation that technological capability has emerged elsewhere. That confirmation alone would transform our civilization's self-understanding and our approach to exploring and settling space. Because one of the implications of detecting extraterrestrial technology would be the realization that the galaxy might contain not just life, but networks of communication or travel between civilizations. If one species achieved interstellar capability and sent probes throughout the galaxy, others might do the same. The space between stars might contain not just natural objects, but also artificial ones, probes, relays, perhaps even autonomous explorers that have been operating for millions of years. In such a scenario, our solar system could be not isolated, but rather part of a broader galactic community that we've only begun to detect. Atlas might be one of many such visitors, most of which we've missed because we weren't looking carefully enough or didn't have the instruments to detect them. Our growing capability to identify and track interstellar objects might be opening our eyes to a reality that has always existed but remained invisible to us. This possibility generates both excitement and caution among those who think seriously about it. Excitement because contact with extraterrestrial intelligence would be the ultimate confirmation that we're not alone, that the universe contains other minds asking similar questions about existence and purpose. Caution because we have no framework for understanding what such contact might mean or how we should respond to it. Our only template for first contact is fictional, the scenarios imagined by science fiction writers and filmmakers. Those scenarios range from the benevolent, enlightened aliens sharing knowledge and technology, to the catastrophic, invasive species seeking to exploit or eliminate us, to the merely indifferent, cosmic intelligences so advanced that humans are beneath their notice. None of these fictional templates are necessarily reliable guides to how actual contact might unfold. The SETI community, researchers involved in the search for extraterrestrial intelligence, has developed protocols for what should happen if we detect a confirmed signal from an extraterrestrial civilization. These protocols emphasize careful verification before any public announcement, consultation with international authorities, and thoughtful consideration of whether and how humanity should respond. But these protocols were developed with radio signals in mind, not physical objects passing through our solar system. If Atlas is confirmed to be artificial, we'd be in uncharted territory procedurally, as well as scientifically. Who decides how humanity responds? What would a response even mean? Attempting to communicate with the object, sending a mission to intercept it, preparing for the possibility of more direct contact? These questions have no established answers, no precedent to guide decision-making. For now, such concerns remain hypothetical. The overwhelming likelihood is that Atlas is natural, however unusual its properties might be. But the very fact that we're asking these questions, that they're being discussed seriously by credible scientists rather than dismissed as pure fantasy, marks a shift in how we think about our cosmic environment. We're living in an age where the extraordinary has become possible, where questions that once belonged entirely to speculation now demand empirical investigation. As we wait for the Mars flyby data to be processed and analyzed, let's turn our attention to what happens next in Atlas's journey through our solar system. The timeline of upcoming events is well established, and each phase offers unique opportunities for observation and discovery. After passing Mars tonight, Atlas will continue its inward trajectory toward the Sun. Its velocity will increase as it falls deeper into the Sun's gravitational well, following the laws of orbital mechanics that govern all objects moving through space. The closer it gets to the Sun, the faster it moves, and the more intense the solar heating becomes. Over the next 3 weeks, ground-based telescopes and space-based observatories will maintain continuous observation as much as possible. Every night that weather permits, every orbital window where space telescopes can point toward Atlas without solar interference, instruments will be recording data. Photometry to track brightness variations, spectroscopy to monitor the composition and intensity of outgassing, polarimetry to analyze how light scatters from the surface, and coma. Every technique that might reveal additional information about the object's nature will be employed. The intensity of observation will increase as perihelion approaches. That's the moment of closest approach to the Sun, currently calculated to occur on October 24, 2025, just 3 weeks from tonight's Mars flyby. At perihelion, Atlas will be approximately 0.6 astronomical units from the Sun, closer than Venus orbits, but not dangerously close. For comparison, Mercury orbits at about 0.4 AU, experiencing far more intense solar heating than Atlas will encounter. But even at 0.6 AU, the solar intensity will be roughly 3 times what Earth receives, and far more than Atlas has experienced during most of its journey through interstellar space. This heating will drive vigorous outgassing, potentially revealing volatile materials that have remained frozen at greater distances. The coma, the cloud of gas and dust surrounding the nucleus, will likely expand significantly. The object's brightness will increase, making it more easily observable even with smaller telescopes. Most importantly, perihelion will provide the best possible conditions for detailed spectroscopic analysis. With maximum outgassing, there will be more material to study, and the increased brightness will allow spectrometers to capture higher resolution data across a broader range of wavelengths. If there are rare or trace constituents in Atlas's composition, that have been difficult to detect at low concentrations, perihelion offers the best chance to find them. The Hubble Space Telescope has been allocated observation time during the perihelion period. Hubble remains one of humanity's most capable instruments for studying distant objects in the visible and ultraviolet portions of the spectrum. While newer space telescopes like James Webb have superior capabilities in the infrared, Hubble's established track record and versatile instruments make it invaluable for studying objects like Atlas. Hubble's observations will focus on several key objectives. High-resolution imaging will attempt to resolve Atlas's nucleus, the solid core beneath the coma, as clearly as possible, potentially revealing details about its shape and surface features. Spectroscopic observations will capture the complete ultraviolet through visible spectrum of the outgassing material, looking for emission and absorption lines that indicate specific molecules and atoms. Time series photometry will track how brightness changes over hours and days, potentially revealing rotation periods or outburst activity. Ground-based observatories will complement Hubble's observations with their own campaigns. Large professional telescopes like the Keck Observatory in Hawaii, the Very Large Telescope in Chile, and the Subaru Telescope in Japan will all dedicate observation time to Atlas. These facilities can achieve extremely high spectral resolution and can observe in wavelength ranges that space telescopes don't cover well, particularly in the near-infrared, where many molecular species have diagnostic features. Amateur astronomers worldwide will also be watching. While they lack the sophisticated instruments of professional observatories, dedicated amateurs with good equipment can make valuable contributions. Time series photometry from multiple locations around the globe can provide nearly continuous coverage, tracking brightness variations that might be missed by professional telescopes with limited observation windows. And occasionally, amateurs make serendipitous discoveries, outbursts, fragmentations, unexpected phenomena that happen to occur while professionals are looking elsewhere. The amateur community has been particularly active in observing Atlas. Online forums and coordination networks have organized observing campaigns, with participants sharing data and comparing results. This distributed approach to observation has become increasingly important in astronomy, where the number of interesting targets far exceeds the available time on professional facilities. Crowdsourced science isn't just a novelty, it's a genuine contribution to our understanding of the cosmos. After perihelion, Atlas will begin its exit from the inner solar system, velocity carrying it back toward the interstellar medium from which it came. The outward journey will provide opportunities to observe how the object behaves as solar heating decreases. Does the outgassing slow gradually or shut off abruptly? Do brightness variations continue or stabilize? Are there any changes in trajectory that suggest continued activity or forces other than gravity? These post-perihelion observations will be challenging as Atlas recedes and dims. Eventually, it will become too faint for all but the largest telescopes to track. There will come a point, probably sometime in mid to late 2026, when we lose sight of it entirely, when even our most sensitive instruments can no longer detect the faint reflected light from this small, distant, rapidly departing object. But before that happens, there's a possibility that we might send a mission. The window for launching an intercept mission is closing, but it hasn't closed yet. If data from the Mars flyby and perihelion observations reveal characteristics that can't be explained naturally, if the case for Atlas being artificial becomes compelling enough, there might be sufficient motivation to mount an emergency mission despite the technical and financial challenges. Such a mission would need to be extraordinarily fast-tracked. Typically, space missions require years of planning, design, construction, and testing. The spacecraft must be designed to withstand launch forces and the space environment. Instruments must be selected and integrated. Flight software must be developed and validated. All of this takes time and involves many stages of review and approval. But rapid response missions are possible when urgency demands. In the 1960s, the United States went from having never sent humans to space to landing on the moon in less than a decade. More recently, China has demonstrated the ability to design, build, and launch lunar missions on compressed timescales. When priorities are clear and resources are committed, space agencies can move quickly. A mission to Atlas would likely be relatively simple by modern standards. The goal wouldn't be to land on the object or orbit it. Matching velocities for those maneuvers would require too much fuel given Atlas's high speed. Instead, the mission would be a fast flyby, with the spacecraft passing close to Atlas at high relative velocity, capturing as much data as possible during a brief encounter window. The spacecraft would need a suite of imaging cameras to photograph Atlas from multiple angles as it approaches and recedes. Different wavelengths, visible, infrared, ultraviolet, would reveal different aspects of the surface and coma. Spectrometers would analyze the composition of outgassing material by passing through the coma. Magnetometers might detect any magnetic field associated with the object. Particle detectors could characterize the dust environment. Even simple instruments could provide data of immense value given the close-range vantage point. The biggest challenge would be navigation and timing. To intercept Atlas, the spacecraft would need to launch at exactly the right time, on exactly the right trajectory, with exactly the right velocity. Small errors in any of these parameters would result in a miss, with the spacecraft passing too far from Atlas to capture useful data. This requires precise knowledge of Atlas's trajectory. One of the purposes of all the observation effort is to refine our orbital models to the point where intercept trajectories can be calculated with confidence. The encounter would be brief, likely just minutes or even seconds of close approach, depending on the relative velocity and trajectory geometry. During that window, onboard computers would execute pre-programmed observation sequences, automatically pointing instruments and triggering measurements without waiting for instructions from Earth. The light time delay, the minutes required for radio signals to travel between Earth and the spacecraft, makes real-time control impossible during fast-moving encounters. Everything must be autonomous. After the flyby, the spacecraft would spend hours or days transmitting the captured data back to Earth. Given the distance and limited transmission power available on a small spacecraft, data rates would be slow. High-resolution images and spectra might take many hours to download completely. But the wait would be worthwhile if the data provided definitive answers about Atlas's nature. As of this writing, no such mission has been officially approved. Space agencies are in wait-and-see mode, evaluating whether the science return would justify the cost and risk. If the Mars and perihelion observations show Atlas to be strange but arguably natural, the case for a dedicated mission becomes harder to make. Resources are limited, and there are many competing priorities for space exploration funding. But if those observations reveal characteristics that push beyond the boundaries of natural explanation, if the chemistry remains inexplicable, if structural features suggest artificial construction, if any smoking gun emerges that can't be dismissed, then the calculation changes. The potential discovery of extraterrestrial technology, even dormant technology, from a long-extinct civilization would be significant enough to justify almost any reasonable expenditure. The question would shift from, should we send a mission, to how quickly can we launch? For now, we watch and wait. The data from tonight's Mars flyby will begin trickling in over the coming days and weeks as researchers process observations and begin extracting scientific results. Initial findings might be announced within days. Simple measurements like brightness and basic spectroscopy that can be quickly analyzed. More sophisticated analyses, detailed modeling of the coma, careful spectral analysis to identify specific molecular species, structural modeling based on brightness variations will take longer, potentially weeks or months. The perihelion observations in 3 weeks will provide another major influx of data. And sometime after that, probably by early 2026, the community will have assembled enough information to draw reasonably firm conclusions about what Atlas is and whether our current understanding of natural objects can adequately explain its characteristics. Until then, the mystery persists. And for those of us watching from Earth, there's something captivating about that uncertainty, about living in a moment when genuine discovery feels possible, when the questions we're asking might have answers that fundamentally change our understanding of our place in the cosmos. While the scientific investigation of Atlas proceeds through observations and analysis, it's worth considering the broader implications of how we study such objects and what our methods reveal about the current state of astronomical science. Because the way we observe and interpret interstellar visitors reflects not just our technological capabilities, but also our conceptual frameworks and the assumptions we bring to the investigation. Modern astronomy is, in many ways, a detective science. We can't touch the objects we study, can't perform direct experiments on them, can't bring them into laboratories for detailed analysis. Instead, we must infer their properties from the light they emit or reflect, from the way they move through space, from the subtle gravitational influences they exert on other bodies. We're cosmic detectives, piecing together evidence from fragmentary clues, building models that might explain what we observe. This indirect approach has proven remarkably successful. We've determined the composition of distant stars by analyzing their spectra, discovering which elements are present based on the specific wavelengths of light they absorb or emit. We've inferred the existence of dark matter, material we can't see directly, from its gravitational effects on visible matter. We've detected planets orbiting other stars by measuring the tiny wobbles they induce in their parent star's motion, or the slight dimming when they pass in front of those stars as viewed from Earth. But indirect inference has its limits, and those limits become especially apparent when studying something as unusual as Atlas. When an object's behavior doesn't match our models, we face an interpretational challenge. Is the object genuinely anomalous, or are our models incomplete? Are we seeing something unprecedented, or are we simply misunderstanding what we're observing? This ambiguity is inherent to the scientific process. Models are always approximations, simplifications of reality that capture important features while ignoring or averaging over details. They work well within the range of conditions where they were developed and validated. But when we encounter something outside that range, something formed under different conditions, something exhibiting properties we haven't previously observed, our models may fail to accurately represent what's happening. The challenge with Atlas is determining whether its unusual characteristics reflect the limitations of our models, or whether they indicate something genuinely outside the realm of natural phenomena as we understand them. The Six Sigma deviation in chemistry could mean our models of cometary formation are missing important physics, or it could mean Atlas isn't a natural comet. The size uncertainty could reflect limitations in our observational techniques, or it could indicate structural complexity that defies simple categorization. The statistical improbability of finding such an object so early could be just that, improbable but possible luck, or it could suggest selection effects or purposeful trajectory we haven't recognized. Scientists generally prefer to exhaust natural explanations before invoking extraordinary ones. This methodological conservatism serves us well, preventing premature conclusions based on incomplete data. But it can also create inertia, resistance to recognizing when something genuinely unprecedented is occurring. The history of science includes examples of both. Phenomena that initially seemed inexplicable but yielded to conventional understanding once we gathered more data, and phenomena that required fundamental revisions to our theoretical frameworks. Pulsars, rapidly pulsating radio sources discovered in 1967, initially seemed so artificial in their precise timing that they were jokingly called LGMs for little green men. But they turned out to be entirely natural, rapidly rotating neutron stars with strong magnetic fields, emitting beams of radio waves that sweep past Earth like a cosmic lighthouse. The initial mystery was solved through better understanding of extreme physics, not through invoking intelligence. Conversely, the accelerating expansion of the universe, discovered in 1998 through observations of distant supernovae, required introducing entirely new physics. Dark energy, a mysterious force that apparently fills space and drives cosmic acceleration. This wasn't artificial intelligence or intervention. It was natural, but fundamentally different from anything in our prior understanding. Sometimes reality does surprise us with phenomena that require genuine paradigm shifts. Where does Atlas fall in this spectrum? Is it a pulsar situation, seemingly inexplicable now, but ultimately natural once we understand it properly? Or is it a dark energy situation, genuinely novel, requiring us to expand our understanding of what's possible? Or might it be something else entirely, perhaps the first confirmed detection of extraterrestrial technology? The answer won't come from a single observation or analysis. It will emerge gradually from the accumulation of evidence, from multiple independent lines of investigation that either converge on a consistent explanation or persistently refuse to fit together. The Mars flyby data is one piece. The perihelion observations will be another. Follow-up studies over coming months will add more. Eventually, a picture will emerge that either makes sense within our current frameworks or demands that we revise those frameworks. One aspect of the Atlas investigation that deserves attention is the international cooperation it has fostered. Astronomy has always been somewhat international in character. The night sky is a shared resource, visible to observers worldwide, and important discoveries are quickly communicated across national boundaries. But interstellar objects have intensified this cooperation because they're transient targets that require coordinated observation from multiple facilities. When Atlas was first detected, observatories around the world immediately began contributing follow-up observations. Facilities in Chile, Hawaii, the Canary Islands, Arizona, Australia, South Africa, every major observatory with capability to observe the object has participated in the campaign. Data is shared through established networks, with researchers analyzing observations from multiple telescopes to build comprehensive understanding. This cooperation extends to space-based assets as well. Hubble is operated by NASA and ESA jointly. Mars orbiters come from NASA, ESA, and other national agencies. Data from these spacecraft is shared among researchers worldwide, though sometimes with proprietary periods where the teams that proposed observations have exclusive access before wider release. The international scientific community is remarkably good at this kind of cooperation. National rivalries and political tensions exist, certainly, but they rarely interfere significantly with collaborative research on shared targets of interest. There's a culture of openness, of building on each other's work that transcends political boundaries. This gives some hope that if Atlas does turn out to be something extraordinary, something that raises questions beyond pure science, humanity might be capable of addressing those questions collectively, rather than fragmenting into competing national responses. Though it's worth noting that this optimism about international cooperation assumes that we're dealing with something that doesn't present immediate threats or opportunities. If Atlas were to exhibit capabilities that suggested it could be dangerous, or if it appeared to contain technology that could be exploited for advantage, the dynamics might change rapidly. History suggests that when security concerns or economic opportunities are at stake, cooperation often gives way to competition. For now, fortunately, Atlas presents neither threat nor obvious opportunity. It's passing through our solar system at high speed, showing no signs of deviating toward Earth or exhibiting capabilities beyond gentle outgassing. Even if it is artificial, it appears to be following a predetermined trajectory without responding to our presence. There's no indication it's here to harm us or that we could extract anything useful from it, even if we wanted to. So the investigation can proceed as pure science, motivated by curiosity rather than fear or greed. This brings us to a deeper question about what we hope to learn from studying Atlas and interstellar objects in general. What's the scientific value of investigating these cosmic visitors? What do they tell us that we can't learn from studying objects native to our own solar system? The answer lies in the concept of comparative planetology, understanding our own system by comparing it to others. Every planetary system forms from a collapsing cloud of gas and dust, but the specific conditions during formation vary. The mass of the parent star, the composition of the nebula, the presence or absence of nearby massive planets, the history of collisions and gravitational interactions, all these factors influence what kinds of objects form and what characteristics they have. Our solar system gives us one example of how this process works. We can study the compositions of solar system comets and asteroids, determining what materials were available during formation and how they were distributed. We can analyze meteorites that fall to Earth, reading their chemical and isotopic signatures to understand the conditions and timescales of their formation. We can observe how comets behave as they approach the Sun, learning about the volatile compounds they contain and how those compounds sublimate. But we're limited to this single example. We don't know how much of what we observe is universal, common to all planetary systems, and how much is specific to the particular conditions under which our solar system formed. Are solar system comets representative of comets everywhere, or are they just one variation on a theme that might be expressed very differently elsewhere? Interstellar objects provide answers. Each one is a sample from another system, carrying information about formation conditions elsewhere in the galaxy. By comparing interstellar visitors to solar system natives, we can begin to distinguish universal characteristics from local peculiarities. We can see what varies and what remains constant, building a more complete understanding of planetary system formation generally rather than just our specific case. Oumuamua taught us that not all interstellar objects behave like typical solar system comets. Its lack of visible outgassing, despite showing non-gravitational acceleration, suggested composition or structure different from what we're familiar with. Whether it was an elongated rock, a hydrogen iceberg, or something else entirely remains debated, but it certainly wasn't a typical comet. Borisov, by contrast, looked quite familiar, a conventional comet with strong water and carbon monoxide emission, behaving much like solar system comets do. This suggested that cometary formation isn't entirely unique to our system, that similar processes occur elsewhere and produce similar results. Now Atlas presents a third data point, and it's ambiguous, partly familiar, partly strange. The outgassing activity suggests comet-like composition, but the chemistry is wrong. The size and behavior have some parallels to solar system objects, but with peculiarities that resist simple categorization. It's expanding our understanding of what's possible, but in ways that create more questions than answers. This is actually how science often progresses. We don't move smoothly from ignorance to knowledge. We move from simpler questions to more sophisticated ones, from crude models to refined ones. Each discovery doesn't just answer existing questions. It reveals new questions we didn't know to ask. Atlas is teaching us that interstellar space contains greater diversity than we anticipated, that objects passing between stars might have characteristics we hadn't imagined, that our sample size of 3 is still far too small to draw general conclusions. If we eventually send a mission to Atlas and determine definitively what it is, natural or artificial, familiar or exotic, that will answer important specific questions about this object. But it will also raise broader questions about what else is out there, what other kinds of objects might be wandering between stars, what surprises await as we improve our ability to detect and study these cosmic travelers. And that's the real value of studying Atlas, not just learning about one specific object, but beginning to map the territory of interstellar space, understanding what exists in the vast distances between stars. That knowledge will inform future exploration efforts, shape our expectations about what we might encounter, As humanity eventually ventures beyond our own solar system and deepen our understanding of how the galaxy works as a dynamic, interconnected system, rather than a collection of isolated stellar islands. As we continue to wait for the processed data from the Mars flyby, it's valuable to examine what the detection and study of interstellar objects tells us about the future of astronomy and space exploration. Because the ability to identify and track objects like Atlas represents a relatively new capability, and one that's rapidly improving with each passing year. Just 2 decades ago, we lacked the technology to reliably detect interstellar visitors. Our telescopes were capable enough, but the automated survey systems needed to scan large portions of the sky repeatedly. Comparing images to identify moving objects didn't exist with sufficient coverage and sensitivity. Objects like Atlas could have passed through our solar system unnoticed, visible in principle, but never actually observed, because no telescope happened to be pointed at the right patch of sky at the right time. The development of automated sky survey systems has changed this situation dramatically. Projects like Pan-STARRS in Hawaii, the Catalina Sky Survey in Arizona, and the Atlas system that detected our current visitor are designed to scan the entire visible sky repeatedly, looking for anything that moves or changes. These systems generate enormous amounts of data, millions of observations each night, that must be processed by sophisticated software to identify interesting objects among the overwhelming background of known stars and galaxies. This automated approach has revolutionized astronomy. We're no longer limited to studying objects we deliberately choose to observe. Instead, we're discovering objects we didn't know existed, finding surprises that reveal phenomena we hadn't anticipated. Interstellar visitors are perfect examples of this discovery mode. They're too rare and too transient to find through targeted searches, but automated surveys catch them as they pass through our cosmic neighborhood. The next generation of survey systems will be even more capable. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations in the next few years with a telescope and camera system designed to image the entire southern sky every few nights. The sheer volume of data it will generate, estimated at tens of terabytes per night, will require advanced computational infrastructure just to process and analyze. With such systems online, our detection rate for interstellar objects should increase dramatically. Instead of finding one every few years, we might detect several per year or even per month. This would rapidly build a statistical sample large enough to begin drawing meaningful conclusions about how common these visitors are, what range of properties they exhibit, and whether objects like Atlas are rare oddities or represent one example of many strange interstellar wanderers. This improved detection capability has interesting implications for the question of artificial objects. If interstellar space contains probes or vessels from extraterrestrial civilizations, and if such objects occasionally pass through our solar system, then better surveys should eventually detect them, assuming they're present at detectable numbers, and that they're distinguishable from natural objects. The challenge is that distinguishing artificial from natural becomes harder, not easier, as we discover more diversity in natural objects. Each new interstellar visitor that exhibits unusual characteristics expands our understanding of what natural objects can be like. This makes it increasingly difficult to claim that any specific characteristic is so unusual it must indicate artificial origin. The goalposts for "this can't be natural" keep moving as nature demonstrates greater creativity than our models anticipated. This dynamic creates a kind of observational paradox. We need to study many interstellar objects to understand their natural diversity. But the more we study, the broader that natural diversity appears, making it harder to identify anything as definitively artificial. Only an object that exhibits truly unambiguous characteristics, clear signals, deliberate maneuvers, obvious engineering, would stand out unmistakably against an increasingly diverse background of natural phenomena. Atlas sits in this ambiguous middle ground, unusual enough to raise questions, but not so obviously artificial that it forces conclusions. It's expanding our understanding of what natural interstellar objects might be like, while simultaneously remaining strange enough that the artificial hypothesis can't be completely dismissed. This is both frustrating and scientifically valuable. Frustrating because we'd prefer clear answers. Valuable because it's teaching us to be more sophisticated in our thinking about these objects. Looking further ahead, beyond just detecting interstellar visitors, there's the question of how we might actively study them in more detail. We've discussed the possibility of sending a mission to Atlas, but what about longer-term strategies for investigating such objects? One approach that's been proposed is maintaining a fleet of small, ready-to-launch spacecraft that could be deployed quickly when interesting interstellar objects are detected, rather than trying to design, build, and launch a mission. In the few months between detection and departure, these pre-positioned spacecraft would already exist, waiting in Earth orbit or at a Lagrange point for a target worth pursuing. When an interstellar object is detected and characterized enough to calculate its trajectory, mission planners would have a window, perhaps weeks or months, to decide whether it's worth sending one of these pre-positioned spacecraft. If so, the spacecraft would be released from its parking orbit, its trajectory adjusted to intercept the target, and autonomous systems would execute the flyby observation sequence without requiring further intervention. This approach has advantages and challenges. The advantage is speed, being able to respond to opportunities quickly without the long lead time typical of space missions. The challenge is cost and commitment. Maintaining a fleet of spacecraft in standby mode requires ongoing investment, with no guarantee they'll ever be used. Space agencies already face difficult choices about how to allocate limited budgets. Adding standing readiness missions to the list of funding demands creates additional pressure, but the potential payoff could be substantial. If we had such a capability, we wouldn't need to debate whether Atlas warrants a dedicated mission. We'd simply deploy a pre-positioned spacecraft, gather the data, and move on to the next target when it appears. Over time, we'd build a comprehensive survey of interstellar objects, visiting dozens or hundreds of them, rather than relying solely on remote observation. Another strategy that's been discussed is positioning spacecraft at advantageous locations for observing interstellar visitors as they pass through. Rather than trying to intercept fast-moving targets, we'd place observatories at locations where interstellar objects are likely to pass relatively close, perhaps in the outer solar system where trajectories converge, or at gravitational lensing positions where the sun's gravity focuses light from distant sources. These positioned observatories would be permanently stationed, continuously monitoring for approaching objects and automatically beginning detailed observations when visitors are detected. They'd have advantages over Earth-based observation: no atmospheric interference, ability to observe continuously without day-night cycles, positions that might provide better viewing geometry than Earth's location. The technology for such missions exists or is under development. Small, capable spacecraft can be built with modern electronics miniaturization. Solar panels or nuclear power sources can provide energy. Autonomous systems can handle observation and data transmission without constant human intervention. What's lacking isn't capability, but commitment, the decision to invest resources in this kind of ongoing interstellar object survey program. That decision might become easier as public and political interest in these objects grows. Atlas and its predecessors have captured attention precisely because they're mysterious, because they raise questions about what else might be out there. If that interest translates into support for more ambitious investigation programs, we might see the kind of infrastructure developed that would make studying interstellar visitors routine rather than exceptional. There's also the interesting question of what happens when we eventually achieve the capability to leave our own solar system and explore interstellar space directly. Objects like Atlas are traveling between star systems on journeys that last millions of years, but with sufficiently advanced propulsion, perhaps fusion drives or antimatter engines or technologies we haven't yet developed, such journeys could be shortened dramatically. Imagine a future where humanity has the capability to send missions to nearby star systems, reaching them in decades or centuries rather than millions of years. In such a future, we'd be creating our own interstellar objects, spacecraft that would pass through other stellar systems, much as Atlas is passing through ours. How would we design such spacecraft? What characteristics would they have? And most intriguingly, would they appear natural to civilizations observing them, or would their artificial nature be obvious? These questions are speculative, certainly, but they're not entirely idle, because our own attempts to explore interstellar space will inform our thinking about what to look for when searching for evidence of others doing the same. If we find that making an interstellar probe look natural is either very difficult or unnecessary, that affects our assessment of whether Atlas might be artificial. If we discover that certain design choices are essentially inevitable for interstellar missions, certain materials, certain geometries, certain behaviors, then we can search for those signatures in objects we observe. The field of interstellar archaeology, studying the possible artifacts of past or present civilizations scattered through the galaxy, is still largely theoretical. We have no confirmed examples of such artifacts to analyze. But every interstellar object we detect and study contributes to our understanding of what's out there, building a baseline against which truly anomalous objects might eventually be recognized. Atlas is part of that baseline building process. Whether it's natural or artificial, studying it advances our knowledge. If natural, it teaches us about the diversity of objects that travel between stars. If artificial, it provides our first confirmed example of extraterrestrial technology. Either outcome is scientifically valuable, though obviously one would be far more profound in its implications than the other. As we approach the end of the third week of October 2025, with perihelion just days away now. The astronomy community is preparing for the next phase of intensive observation. Telescope time has been allocated. Observation plans have been finalized. Researchers have cleared their schedules to be available for rapid analysis of incoming data. This is the culmination of more than a year of anticipation since Atlas was first detected. Whatever the perihelion observations reveal, they will represent our best view of this object. After that, Atlas will recede into the distance, growing fainter and harder to observe with each passing day. Within months, it will be lost to all but the most powerful telescopes. Within a year or two, it will be gone entirely, continuing its journey through interstellar space toward whatever distant destination lies ahead. This transience adds poignancy to our investigation. We have one chance to study Atlas in detail, one brief window when it's close enough for thorough observation. Miss that window, make mistakes in our analysis, fail to capture crucial data, and we lose the opportunity forever. This object won't be coming back. It's a one-time visitor to our cosmic neighborhood, and we need to learn everything we can while it's here. The sense of urgency surrounding the Atlas observations reflects a broader truth about astronomy. We're often operating at the mercy of cosmic timing. Objects don't appear on our schedule. Phenomena don't wait for us to be ready. The universe unfolds according to its own rhythms, and we must adapt our observation strategies to match those rhythms, rather than trying to impose our preferred timelines on natural events. This creates interesting challenges for both professional and amateur astronomers. Professional facilities must balance the demand for observation time between long-planned programs and targets of opportunity like Atlas. A major telescope might have its observation schedule planned months or even years in advance, with every night allocated to specific projects that have been through competitive proposal processes. When something unexpected appears, accommodating it requires disrupting those carefully laid plans, potentially disappointing researchers whose approved projects get delayed. But most observatories recognize that some targets are too important or too time-sensitive to ignore. Interstellar objects fall into this category, as do supernovae, gravitational wave events, asteroid approaches, and other transient phenomena. So mechanisms exist to request directors' discretionary time, blocks of observation that can be allocated quickly without going through normal proposal channels. Atlas has benefited from such discretionary allocations at multiple facilities. Amateur astronomers operate with more flexibility in some ways, less in others. They don't need to navigate bureaucratic approval processes or compete for telescope time. If they own equipment and the weather cooperates, they can observe whatever they choose. But they're limited by equipment capabilities and by the practical constraints of their own time and resources. Someone observing from their backyard can't match the light-gathering power or instrumental sophistication of professional facilities. Yet amateurs contribute meaningfully to Atlas studies and interstellar object research generally. Their observations fill temporal gaps between professional campaigns. They provide geographic diversity, observing from locations around the world that complement professional facilities. And occasionally, they catch phenomena that professionals miss: outbursts, brightness changes, unexpected events that happen when large telescopes are pointed elsewhere. The collaboration between professional and amateur astronomers has strengthened over recent decades as communication technology has improved. Online forums, data sharing platforms, and coordination networks allow rapid dissemination of observations and findings. An amateur in Australia can detect something unusual about Atlas, and within hours, professionals in Chile or Hawaii are confirming and following up with more sophisticated instruments. This distributed collaborative approach makes the whole community more effective than either segment could be alone. Social media has also played an interesting role in how astronomical discoveries are communicated and discussed. In the past, significant findings would be published in professional journals months or years after initial observation, with public awareness coming much later through press releases and popular science coverage. Now, initial observations often appear on social media within hours or days, with researchers sharing preliminary findings informally before formal publication. This has advantages and disadvantages. The advantage is speed. Interesting discoveries get communicated quickly, allowing rapid coordination of follow-up observations and faster scientific progress. The disadvantage is quality control. Preliminary results might be wrong, and informal communication can lead to misunderstandings or premature conclusions that then get amplified before they can be corrected. Atlas has been discussed extensively on social media since its discovery, with both professional astronomers and interested laypeople sharing observations, interpretations, and speculation. This public dialogue has raised awareness of the object and generated interest that might not have existed if information had been restricted to formal publications. But it's also led to some confusion, with preliminary measurements being cited as definitive facts and speculative hypotheses being presented as established conclusions. Navigating this communication landscape requires care. Researchers need to be honest about uncertainties, while avoiding language that might be misinterpreted. They need to share findings quickly enough to be useful, while not overclaiming based on incomplete data. And they need to engage with public interest without encouraging unfounded speculation or sensationalism. The question of Atlas's possible artificial nature illustrates these challenges perfectly. Most scientists studying the object believe it's natural, despite its unusual characteristics. But most also acknowledge that certainty is impossible with current data. There's a small but non-zero probability that it might be artificial. How do you communicate that nuanced position to a public that often prefers definitive answers? If you emphasize the likelihood that Atlas is natural, you risk being accused of closed-mindedness or dismissing possibilities without adequate investigation. If you emphasize that artificial origin can't be ruled out, you risk encouraging speculation that runs far ahead of the evidence and creates expectations that are unlikely to be fulfilled. The middle ground, honest acknowledgement of uncertainty, is scientifically appropriate but less satisfying for people seeking clear answers. This communication challenge isn't unique to Atlas. It arises whenever science encounters something unusual that captures public imagination. The discovery of pulsars, the detection of cosmic microwave background radiation, the identification of dark energy, all involved periods of uncertainty where multiple interpretations competed and public communication required carefully balancing honesty about unknowns with explanation of what was and wasn't plausible. In the specific case of interstellar objects, and the possibility of artificial origin, there's additional sensitivity because of the broader context of searching for extraterrestrial intelligence. SETI, the search for extraterrestrial intelligence, has a complex relationship with mainstream astronomy. It's scientifically legitimate in principle, but it's also associated with fringe speculation and has historically struggled to receive funding and institutional support. Many astronomers are wary of discussing ATLAS in terms that might seem to align with SETI, fearing that it would damage their credibility or invite ridicule from colleagues. This creates pressure to emphasize natural explanations, even when data is ambiguous. The scientific community's culture of conservatism and skepticism, generally valuable for maintaining quality standards, can sometimes become an obstacle to seriously considering unconventional possibilities. But there's also a counter-pressure from those who feel that artificial intelligence in the galaxy is plausible enough that we should take seriously any object that exhibits unusual characteristics. They argue that dismissing the possibility without thorough investigation is itself a form of bias, an unwillingness to follow evidence where it leads because we're uncomfortable with implications. The reality is probably that both perspectives have merit. We should be skeptical and require strong evidence before accepting extraordinary claims. But we should also remain open to unconventional explanations when conventional ones consistently fail to fit observations. The challenge is maintaining that balance, neither jumping to sensational conclusions nor rejecting possibilities prematurely. As perihelion approaches and observation intensity increases, these tensions around interpretation and communication are likely to intensify. If the perihelion data reveals characteristics that further deepen the mystery, if ATLAS continues to resist conventional explanation, then pressure will grow to either accept that we simply don't understand interstellar object diversity as well as we thought, or to seriously consider whether we might be dealing with something artificial. Neither option is comfortable for the scientific community. Admitting that we don't understand something that seems like it should be comprehensible is humbling, especially in a field that prides itself on having developed sophisticated models of cosmic phenomena. But accepting that an object might be artificial carries even larger implications, requiring careful justification to avoid appearing credulous or sensation-seeking. The ideal outcome, from a scientific standpoint, would be data so clear that interpretation becomes straightforward. If perihelion observations show that ATLAS's chemistry can be explained by specific formation conditions we hadn't previously considered, if its size and structure fit models we've now refined, if all the anomalies resolve into natural phenomena once we have better data, then the mystery dissolves and we simply add ATLAS to our catalog of interesting but ultimately natural objects. Alternatively, if observations reveal unambiguous characteristics that can't be natural, clear geometric patterns in surface features, artificial materials, deliberate signals, obvious engineering, then we'd have definitive evidence requiring fundamental reframing of our understanding of the galaxy as a populated environment where technological artifacts travel between stars. But the more likely outcome is continued ambiguity. Real observations rarely provide the clarity we'd prefer. Data comes with uncertainties, measurements conflict, interpretations depend on assumptions that themselves are uncertain. we'll probably end up with improved understanding of Atlas, but not complete understanding, better constraints on its properties, but not definitive answers to all questions. And that's actually normal for science at the frontier of knowledge. We're accustomed to textbook science where questions have clear answers and phenomena are well understood. But at the research frontier, ambiguity is the rule rather than the exception. Progress comes through gradually reducing uncertainty, building confidence in some explanations, while eliminating others, moving from complete ignorance toward partial understanding, rather than making sudden leaps to perfect clarity. Atlas represents precisely this kind of frontier research. We're studying something we don't fully understand, using methods that have limitations, working with data that's incomplete. The scientific process will eventually provide better answers, but that process takes time and requires patience. The Mars flyby data is one step. The perihelion observations will be another. Follow-up studies over subsequent months will add more pieces to the puzzle. Gradually, a picture will emerge. Maybe it will show Atlas as a strange but natural object, expanding our understanding of cometary diversity. Maybe it will reveal characteristics that demand we seriously consider artificial origin. Maybe it will simply remain enigmatic, an object we never quite understand before it departs our observable range. Whatever the outcome, the investigation of Atlas is contributing to human knowledge. We're learning about interstellar space, about the objects that travel between stars, about the diversity of matter and phenomena beyond our solar system. We're developing techniques for studying transient targets. We're building infrastructure for detecting and characterizing interstellar visitors. And we're confronting fundamental questions about what's possible in the universe and how we recognize the truly unprecedented when we encounter it. These contributions have value regardless of whether Atlas turns out to be natural or artificial, ordinary or extraordinary. Science progresses through accumulated knowledge, through building understanding piece by piece. Every observation contributes to that accumulation. Every analysis refines our models. Every discovery, whether revolutionary or incremental, advances human comprehension of the cosmos. As we near the end of our exploration of the Atlas mystery, it's worth reflecting on what makes stories like this so captivating to those of us who follow astronomical discoveries. There's something fundamentally compelling about the unknown, about questions that don't yet have answers, about mysteries that challenge our understanding of reality. Atlas taps into some of humanity's deepest curiosities. Are we alone in the universe? What exists in the vast spaces between stars? How much do we really understand about the cosmos we inhabit? These aren't just academic questions. They touch on fundamental issues of meaning, purpose, and our place in the grand scheme of existence. For thousands of years, humans have looked at the night sky and wondered what lies beyond the familiar patterns of stars and planets. Ancient astronomers mapped the heavens, noting the movements of celestial bodies and seeking patterns that might explain cosmic order. They didn't have our telescopes or spacecraft, our spectroscopes or computer models, but they had the same curiosity, the same drive to understand what exists beyond the boundaries of direct experience. We're heir to that tradition of curiosity. We have vastly superior tools now, instruments that can detect objects billions of light years away and analyze their properties in exquisite detail. but we're driven by the same fundamental impulse that motivated those ancient stargazers: the desire to know, to understand, to push back the boundaries of ignorance and mystery. Interstellar objects like Atlas are particularly fascinating because they're tangible visitors from beyond, physical objects we can actually observe and study rather than just distant points of light. They've traveled across the galaxy, carrying information about places we can never directly visit. Their messages in bottles, cast into the cosmic ocean by whatever processes, natural or possibly artificial, sent them on their journeys. Every time we detect one of these visitors, we're receiving a message from the broader galaxy. Sometimes that message is clear. Borisov told us that comets form in other stellar systems, much as they do in ours, that the basic chemistry and physics we observe locally applies elsewhere as well. Sometimes the message is cryptic. Oumuamua raised more questions than it answered, leaving us uncertain about what we'd actually observed. And sometimes, as with Atlas, the message is ambiguous, requiring careful analysis to determine what it's actually telling us. If you followed this journey through the Atlas story, if you found yourself intrigued by the questions we've explored and the mysteries we've encountered, then I invite you to subscribe to this channel, because stories like this one are unfolding continuously as our understanding of the cosmos deepens. New discoveries happen regularly, sometimes incremental, sometimes revolutionary, and staying connected means you'll be among the first to learn about them. Hit that subscribe button now, and you'll join a community of curious minds exploring the frontiers of human knowledge. You'll get updates as the Atlas story develops, as perihelion observations are completed and analyzed, as we learn more about what this mysterious visitor actually is. And you'll be here for the next big discovery, whatever it might be, the next interstellar object, the next exoplanet that might harbor life, the next breakthrough that changes how we understand our place in the universe. But more than just receiving updates, subscribing means becoming part of a conversation. The comments section on these videos creates a space where people from around the world share their thoughts, ask questions, propose ideas, and collectively work through the implications of new discoveries. Some of the most interesting insights come not from professional researchers, but from thoughtful viewers who bring fresh perspectives and ask questions that experts might overlook. I read the comments carefully, and they often shape future content. When viewers express particular interest in certain aspects of a story, I explore those aspects in more depth. When questions arise that need clarification, I address them in follow-up discussions. This isn't one-way communication. It's a dialogue between someone who spends considerable time synthesizing information and a community of people who engage thoughtfully with that information. So as we continue exploring the Atlas mystery and await the crucial perihelion observations, your participation matters. Your questions, your insights, your perspectives contribute to our collective understanding. And subscribing ensures you remain part of this ongoing exploration as it unfolds in real time. Now, as we prepare to conclude this documentary, let's consider what the next few weeks might bring. Perihelion is scheduled for late October, just days away from when many of you will be hearing these words. The observation campaigns are ready. Hubble has its schedule prepared. Ground-based observatories have allocated time. Amateur astronomers worldwide are preparing their equipment. When perihelion occurs, Atlas will be at its most active, most observable, most revealing. Solar heating at that close distance will drive maximum outgassing, potentially exposing materials that haven't been visible at greater distances. The coma will expand, providing more material for spectroscopic analysis. Brightness will increase, allowing higher resolution observations and detection of fainter features. If there are surprises waiting in Atlas's composition, trace elements that haven't been detected yet, unusual isotopic ratios that might reveal formation conditions, unexpected molecular species that could indicate exotic chemistry. Perihelion is when we're most likely to find them. If there are structural features that have been too subtle to detect at greater distances, surface patterns, regular geometries, signs of internal complexity, they might become visible in the enhanced observations during closest solar approach. The data collection phase will be intense but relatively brief. Perihelion itself is a single moment, but the period of peak activity and optimal observation extends for perhaps a week on either side. During those 2 weeks, every available instrument will be capturing data continuously whenever conditions permit. Then, as Atlas begins receding from the Sun, activity will gradually decrease, and the object will slowly fade from view. Processing and analyzing that flood of data will take much longer. Initial results, basic measurements like brightness curves and simple spectra, might be available within days, but sophisticated analysis, detailed compositional modeling, structural interpretation, comparison with theoretical predictions, will take weeks or months. Some results might not be published until 2026 or even later, as researchers carefully verify their findings and prepare formal papers for peer review. So, we're entering a period of anticipation, followed by gradual revelation. The next few weeks will see the actual observations being made. The months following will see those observations being transformed into scientific understanding through analysis and interpretation. And throughout that process, the broader community, researchers, enthusiasts, curious observers, will be watching, discussing, debating what the findings mean. This is how science works at the frontier, not through sudden breakthroughs that instantly answer all questions, but through patient accumulation of evidence, careful analysis, and gradual convergence toward understanding. It requires both intellectual rigor and tolerance for uncertainty, both confidence in methods and humility about limitations. Atlas may ultimately be explained entirely through natural processes we already understand or can easily extend. The unusual chemistry might reflect formation conditions that are rare but not impossible. The size uncertainty might be resolved through better observations, revealing a structure that fits known categories. The statistical coincidence of finding such an object early might simply be luck. Improbable things do occasionally happen. Or Atlas might force us to expand our understanding in more fundamental ways. Perhaps it will reveal that interstellar space contains greater diversity of objects than we anticipated, that the range of possible cometary compositions is broader than solar system examples suggested. Perhaps it will demonstrate processes or phenomena we hadn't previously recognized, expanding our catalog of what nature can create. Or, and this remains the remote but captivating possibility, perhaps Atlas will turn out to be something genuinely unprecedented, something that challenges the assumption that all objects traveling between stars are natural. Perhaps the artificial hypothesis, currently entertained only as an unlikely alternative, to be considered seriously only if all natural explanations fail, will become unavoidable as data accumulates. We won't know which of these paths we're on until the evidence is in and has been thoroughly analyzed. And that uncertainty, that sense of standing at a threshold where genuine discovery is possible, is part of what makes this moment special. We're living through a time when the answer to fundamental questions about the nature of interstellar space, about the prevalence of intelligence in the galaxy, about what's possible in the cosmos, might actually change based on observations being made right now. Whatever Atlas turns out to be, studying it represents humanity doing what we do best: observing, questioning, analyzing, seeking to understand. We're a curious species, driven to explore and comprehend. We've used that drive to build civilizations, develop technologies, expand our knowledge from immediate surroundings to encompass the entire observable universe. Every discovery, every answered question, every mystery solved is a testament to that enduring human quality, the refusal to accept ignorance when understanding is possible. Atlas will eventually leave our solar system, continuing its journey through the galaxy toward whatever distant destination its trajectory carries it toward. But the knowledge we gain from studying it will remain with us, integrated into human understanding of the cosmos. Whether that knowledge is revolutionary or incremental, whether it forces paradigm shifts or simply adds details to existing frameworks, it becomes part of our collective comprehension of reality. And that's the real story here, not just what Atlas is, but what the process of studying it reveals about who we are. We're the species that looks at mysterious visitors from the depths of space and asks, "What are you?" We're the civilization that builds instruments to answer that question, that develops methods to extract information from faint reflections of starlight, that works together across national and cultural boundaries in pursuit of shared understanding. We're standing on Mars with our robotic orbiters, watching Atlas pass by. We're stationed beyond Earth's atmosphere with Hubble, preparing to capture perihelion in unprecedented detail. We're scattered across the planet at countless telescopes, professional and amateur, all pointed at the same target, all contributing pieces to a puzzle that we're solving together. That collective effort, that shared pursuit of knowledge, is perhaps the most hopeful aspect of the entire endeavor, because whatever challenges humanity faces, whatever divisions or conflicts occupy our attention, we're also capable of this, of coming together to explore, to learn, to push the boundaries of understanding. The curiosity that drives us to study Atlas is the same quality that might ultimately carry us to the stars ourselves, that might transform us from a single-planet species into a cosmic civilization exploring the galaxy. For now, we watch and wait. We gather data and analyze results. We discuss and debate, propose and test hypotheses, gradually build understanding from accumulated observations. And in doing so, we participate in one of humanity's grandest endeavors, the ongoing attempt to comprehend the universe we inhabit and our place within it. The story of Three-Eye Atlas is still being written. The next chapters will unfold over the coming weeks and months as perihelion observations are completed and analyzed. Whatever those chapters reveal, they'll add to the larger narrative of human exploration and discovery, a narrative that stretches back to our ancestors, first wondering about the lights in the night sky, and extends forward to a future we can barely imagine, where questions that seem mysterious today will be answered and new mysteries will have emerged to captivate future generations. Thank you for joining me on this journey through the Atlas mystery. Stay curious, keep looking up, and remember to subscribe so you'll be here for whatever comes next. Because in a universe as vast and surprising as ours, the next great discovery is always just around the corner, waiting to be made by those who take the time to look.